right, so this is 2-6 rational functions part 2 or day 2. Today's essential question is how can I sketch rational functions? So yesterday we talked about some critical features, or in part 1 about domains, what can I use, vertical and horizontal asymptotes, when do they have them? Today we're really going to dig into, okay, how can I make a picture myself? We know we have the graphing technology that we can do something with our calculators or with like something like Desmos, but what if I wanted to make a sketch myself? What are the important features of a graph? So we're kind of going to go back to our chapter 1 conversations about what are important parts of a graph to be able to do that. So that's the essential question that we're going to answer today. How can I sketch the graphs of rational functions? But before we start that, I'm going to do a little warm-up question here to address an issue that's going to happen some today that we need to make sure we remember to deal with when we are solving these. So vertical and horizontal asymptotes. There's a rational function. Let's talk about our degrees. So we're degree 2 on the top, it looks like, and degree 2 on the bottom. So the degrees are equal, so that's going to tell us something. But remember, one of the points we talked about yesterday is that you want to always make sure that your polynomial is reduced, that there are no common factors. So what I'm going to do, and none of them yesterday were there any common factors, but today we're going to start running into that a little bit. So I want to see if you can take a moment, pause the video. Can you please factor the top and the bottom? We're going to need this for what we're going to talk about, so go ahead and pause. Factor the top and the bottom, and then we're going to come back together. Okay, in the denominator, we've got an x and an x. Multiply to 3, add to 4, it would be a 3 and a 1. Everything's positive, so that one's not so bad. Numerator might be harder for people. To get a 3x squared, we have no option but a 3x and an x. What multiplies to a negative 6? We know we're going to have opposite signs. It's either going to be a 1 and a 6 or a 2 and a 3. I think what we want is the 2 and the 3, and I think the 2 needs to go here and the 3 there, and a minus and a plus. Okay, how do I check to make sure that that's right? By the way, neither of those are going to add immediately to that 7 with the signs the way they are, but remember you have to check the outsides plus the insides in FOIL are double distribute there. So outsides will give you a 9x, insides give you a negative 2x, which add together to give you that positive 7x. So just be careful when you're factoring there. It's a really important skill that we need to make sure that we're still confident with. Okay, so why did I have you do that? Well, for a couple reasons. Let's talk about vertical asymptotes first and what's happening in this situation. So in order to calculate a vertical asymptote, we need to make sure that our fraction is simplified. So I'm going to even step back one more, and I'm going to talk about domain. So when I talk about the domain of a function, I'm going to set that denominator equal to 0, and I'm going to solve, right? So to be able to do that, since it's second degree, I would have to do the factoring that you just did, and then I'm going to set those equal to 0 and say, okay, well, I can't use negative 1, and I can't use negative 3, so my excluded values, the things I'm going to leave out of the domain, would be at negative 1 and at negative 3. So the domain of this function would be all real numbers. X can't be equal to negative 1 or negative 3. Now, normally we yesterday would have said, okay, so those are our vertical asymptotes. But here's the thing. If you look at the graph of this, so I'm going to have you go ahead and type in this and take a look at the graph. So go ahead and pause if you need to. Type that in to your graphing calculator. So that equation we just had. I don't see two vertical asymptotes on this. I only see a vertical asymptote happening at that negative, looks like the negative 1. So if I put in our negative 1, and I can go to my table, I'm going to go my table set and start back again at 0. If I go to my table, it's going to say at negative 1 and negative 3, it says error in both those places. Yes, because they're not in the domain of the function. But on my graph, I'm only seeing it approach infinity and negative infinity one time, and that looks like it's only at the negative 1. So what's happening at the negative 3? If you would have just kind of done what you normally did, you would have said there were two vertical asymptotes. There's not. The only vertical asymptote we have on this graph is at x equals negative 1. Something else is happening at negative 3. Take a look back at our original. What I ask you to do is factor. Do you notice that you have a common factor in this polynomial in the numerator and the denominator that would divide out, which would leave you 3x minus 2 over x plus 1. Notice what's left in the bottom, that factor of x plus 1. That's why it's a vertical asymptote. You have to look at vertical asymptotes after you've simplified your equation. So we want to make sure we always simplify. Now, that being said, the domain still excludes both of these. The original function, the domain excludes both. So what's happening on the graph at negative 3? So we want to dig into this a little bit. So if you look at negative 3 on the graph, it looks like it's just part of a curve there. I want to zoom in, so I'm going to adjust my window here. I'm going to make my window and my x values go from negative 5 Oh, not even -5. We'll go -4, make it a little closer to -2. So I'm going to kind of zoom in on that -3. Can you see that little break in the graph there? That little break is called a hole. So we know that the value of the function doesn't exist there. Remember in our piecewise graphs, we talked about those holes and those little breaks like that. So that's what's happening at that location on the graph. So at x equals -3, this is actually called a hole. Sometimes they call it a point discontinuity. So we have a place where it's discontinuous. There's a break in the graph. So it's a place where it's an excluded value of the domain. And we also call it, this is a really important one, a removable, instead of a point, a removable discontinuity. Okay, think about why they might call it removable. You could take out that common factor. So that's why they call it removable. So we're going to be looking for those. Before you can determine, hey, this is my vertical asymptote or vertical asymptotes, we have to always simplify that fraction first. Still not in the domain of the function, right? Still not there. So there's a hole in that original graph if we graph it, but it is definitely not a vertical asymptote. It's a different place. So what if I just graphed this? What would be the difference in the graph? I'm curious if you'd know. If I didn't have that x plus 3 factor in there, how would the graph be different? So I'm going to go ahead and type that one in graph. It looks identical, right? You really can't see the difference, but here's what the difference would be. If I go to my window and kind of zoom in on that -3 spot there, you won't see the hole. Right, but we know from the original that there is a hole there. So that's the difference between the graph then, is that removable discontinuity. So it's really acting like a 3x minus 2 over an x plus 1, but my original function has a hole or removable discontinuity there. Okay, so we've talked about vertical asymptotes. We set the denominator equal to 0 and we solve. We think about the domain, the excluded values, but now we have to remember to keep track of those holes. Make sure that you simplify your fraction to be able to determine them. All right, let's talk horizontal asymptote here. This should be a whole lot easier. You've already looked at the graph as well. We're talking about comparing our degrees. So for horizontal asymptote, the degrees in this case are equal. So the degrees are equal. So it's the same in the top as it is in the bottom. So think back to what that meant. When the degrees were equal, it went to the ratio of the leading coefficients. So the y value would be the ratio of the leading coefficients for each of these fractions or each of those polynomials. So it should be y equals 3. So we should have a horizontal asymptote at y equals 3. If you look back at your, oops, I'll zoom out again here. If you look at your equation or your graph, it sure looks like it's getting closer to 3. You can go to your table and go out further and further and further and just make sure that that makes sense when you think about it, and you'll see that that value looks like it's getting closer to 3. So it's nice to not have to look at the graph to do that. All right, so the little caveat here, removable discontinuities, those points, those holes, be careful in your domain when you look at those. All right, so let's talk about what's critical in sketching, and then we'll practice a few sketches here. What would be important to think about in a sketch? So we're going to go back to what we did in the first chapter, all of the same things that we would talk about in a graph that are important. But for rational, we have to add this extra, find your domain and simplify the fraction if possible. So making sure we know what's excluded first, so the domain, but then also what might be just a hole or removable discontinuity, so we can have an accurate look at that graph. But all the other things that we were doing from before. So we would want to find a y-intercept. So where does the graph cross the y-axis? So finding a y-intercept means you're looking for the value of the function when x is 0. So what happens? So doing that f of 0 and seeing what you get is really helpful. Finding the x-intercept. Okay, so knowing where it crosses the x-axis. So that means setting the equation equal to 0 and solving. So really, in effect, remember what this just means. We're putting in kind of zeros in both spots here and seeing where does it cross the x-axis, where does it cross the y. Really important places. Asymptotes. So we know how to deal with those. Set the denominator equal to 0 and take a look and see what makes that true. Horizontal asymptotes, you're looking at the degrees. So making sure you're doing that degree comparison if it has a horizontal asymptote, and then doing enough additional points that you can see and connect with a smooth curve. So we're going to do a few additional points and connect with a curve so we can see what that looks like. So you might have to make a little table of values and do a few more to kind of fill in the gaps in between. So we're going to build on what we did before using our understanding of what rational functions do. All right, so we're going to start with this one, the 3x over x plus 4, and we're going to think about this this list all the time. So we're going to do whatever we need to understand what's happening here. So let's talk about the asymptotes first, since that's something that I think we've been dealing with a lot in the past couple of days. So degree 1 in the top, degree 1 in the bottom. So the degrees are equal. So since the degrees are equal, let's talk horizontal asymptote for a second. Since the degrees are equal, that means it's going to have a horizontal asymptote, and it's going to go to the ratio of the leading coefficients, which would be 3 over 1. So we're going to have a horizontal asymptote at y equals 3. So what we're shooting for here is we're trying to be able to sketch this ourselves without having to do it on the calculator, but of course we'll sketch it there too. Okay, let's talk vertical asymptotes for a second. Can you tell me the domain of this function? So set the bottom equal to 0. So we get x equals -4. So the domain for this rational function would be all reals. X can't be -4. Can I reduce this fraction at all? Are there any common factors? Well, no. So that means the domain's excluded value of -4 is actually going to be your vertical asymptote. There's no removable discontinuity here. We are stuck with that x plus 4. So our vertical asymptote then is going to be at x equals -4. It's the excluded value for our domain, and I can't remove it. I can't simplify that fraction at all. So I have a vertical asymptote then at x equals 4. Oop, not +4. -4. So over here, 1, 2, 3, 4. All right, so vertical asymptote. This really does help you kind of frame what your graph is going to look like. All right, let's talk about intercepts, because these are really helpful. So we're going to put in 0 for x and solve for y, and see what we come up with here for our y-intercept. So 3 times 0 over 0 plus 4. That looks like 0 over 4, which looks like 0, which means we're going to have the ordered pair 0, 0. I put in 0 for x, I got 0 for y. So 1 point on my graph is going to be 0, 0. Well, unfortunately, that's also going to be the x-intercept point, right? If I set this equal to 0 and tried to solve for x, remember the first thing you would do would be multiply by x plus 4. Well, that's still going to give you just 0 equals 3x, and x would be 0. So you're still going to get that same ordered pair 0, 0. So I only have that one x-intercept. That's not enough to be able to graph the whole thing, right? So the intercepts don't really give you enough of a picture. So that's why they say, hey, let's do some additional points. That means you're making a table of values and finding some other numbers to try. So what might be some good numbers to do? Well, try some on either side of that vertical asymptote so you can see what's happening. It looks like I have points down here in quadrant 4 and a little bit maybe 1, 2, 3, but I need some on the other side as well, like what's happening on the left-hand side of x equals -4. So how about try -5 at least? And then maybe we try, like, I don't know, -1 and 1, see a couple more points there, so we can substitute those in. So you can actually just plug them into the equation and see what you get. So like 3 times -5 over -5 plus 4, and just solve, or you can use your graphing calculator to help. So let's see how we can get a little faster. So I'm going to go ahead and put that in. I'm using my table here, though, so I'm going to make sure my table is starting at 0 so I can see some of these values. Looks like at 1 it was 0.6. I wanted -5. Looks like it was 15. -6 is 9. We can see that's kind of decreasing there. We can get as many values as we need to. -1 was -1. We have some different options to be able to. Was that 15? Yeah, that looks like that would be right. So we can get some other values to kind of get a little bit more of the shape here. So -1, -1. We have 1.6, so that'd be about there. And we can see what's happening in this neck of the woods here. And then on the other side, -5 was, oh my goodness, 15. So way up there, it's going to do something like this. Now, we can put as many more points as we need to get the general shape, but the additional points help us kind of fill in those places in between. So always do points on either side of your vertical asymptotes. If you have multiple vertical asymptotes, do points in all of those regions so you can see where things are happening. So we can get a pretty decent sketch. And if you look back now at your graphing calculator and actually do the graph, you can see we have pretty much exactly the same thing, but we were able to do it ourselves. All right, let's try another one. All right, so we're going to sketch this graph, 3x over x squared minus, or plus x minus 2. So 3x, make it a little bit easier for you to read here, x squared plus x minus 2. All right, so let's do some comparison of degrees here. Degree in the top is 1. The degree in the denominator is 2. Okay, so right away we can talk about horizontal asymptote then. The degree is greater in the bottom. So the degree is greater in the denominator. So if it's bigger in the bottom, remember that means the fraction's going to get closer and closer to 0. So we have a horizontal asymptote then at y equals 0. So immediately I know I'm going to have this. So I have a horizontal asymptote on this graph of y equals 0. Degree is bigger in the bottom. All right, let's talk domain for a second so we can see what's happening here. All right, so the domain of this function, set the denominator equal to 0 to find those excluded values. It's a degree 2. So we have to see if we can solve it by factoring. If it doesn't factor, then we're going to have to try to use quadratic formula, which does happen sometimes, but I think this will work out okay. Multiply to a negative 2, add to positive 1. That would be plus 2 minus 1. And that gives us a negative 2 and a positive 1. So our excluded values, we couldn't use negative 2 and we couldn't use positive 1. So that means the domain of this function is all real numbers, and x can't be negative 2 or 1. All right, now let's just double check and make sure we can't reduce this fraction at all, because if either of those are removable, something that was a common factor, then they wouldn't be vertical asymptotes, they would just be those holes. Well, if I think of this denominator as x plus 2, x minus 1 over 3x, some people just do it right away at the beginning. There's nothing to divide out. That means both of these are going to be vertical asymptotes. So my vertical asymptotes are going to be at x equals negative 2 and also at x equals positive 1. So I have two of them. So I have one at x equals negative 2 and x equals positive 1. So two vertical asymptotes on this one, degree 2. If you had a degree 3 on the bottom, you could have 3 vertical asymptotes. You have all sorts of possibilities. All right, so that gives us a good kind of baseline here. Now we're going to talk about x and y intercepts and see if we have any places where this graph is going to be crossing the x or y axis. So let's start with y-intercept first. That means you're putting in 0 for x. So 3 times 0 over 0 squared plus 0 minus 2. We're going to get 0 over negative 2, which is 0, which means this graph goes through the point 0, 0. Now, this is what freaks people out. 0, 0 is right here. It's on an asymptote. Yes, because horizontal asymptotes, remember, are talking about end behavior, what the ends of the graph approach. It doesn't matter what it's doing around the origin and things like that. So you can definitely have graphs that cross over a horizontal asymptote in lots of different situations. Not vertical ones, but definitely those horizontal, because horizontal asymptotes is end behavior, the ends of the graph. So that's totally fine. I am not bothered by that in the least. X-intercept, remember, we're going to have the same deal happening here. It's just going to be what makes the top 0, which again is just going to be 0. We already have that point. So 0, 0 is our x and our y-intercept. So that gives us a 1 point. Great. That's probably not enough to see the shape of this, right? So we're going to need to do quite a few additional points here to be able to tell what's happening. So think about where we'd want to know some values. I'm going to need to know something to the left of negative 2, so I'm for sure going to need to do something there. I probably need something else between negative 2 and 1 as well. I don't know, like maybe negative 1 for sure. You might even need something else. And you're probably going to need something bigger than 1 as well, because we have no idea what's happening there. So being able to do enough additional points where you can see what's happening is really important. Okay, so I'm going to go ahead and have you pause the video, go to your table, and get some numbers. All right, so we can get some values in here. So I entered in my equation. Looks like negative 2 1/4. And this was a 1.5. This is 1.5. You can definitely get some more in there. So at negative 3, we had negative 2 1/4, so somewhere in there. At negative 1, we had 1.5. And then at 2, we also had 1.5. And we can see some other things that are happening. So you might want to get a few more points in there. We can get as many as we need to. See where the errors are, negative 2 and 1. Those are where your vertical asymptotes are. 3 was 0.9. That might be a nice one to get in there too, so we know it's decreasing. So we have, whoopsie daisy. Sorry about that. That went over my vertical asymptote. Didn't mean that. And then this one is going to do something like this. And this one over here is going to do something like that and approach that end behavior. So we have those 3 different parts of the graph. The additional points is doing as many as you need to get what the shape is. And if I go to my graph, I can see that that picture looks very similar to what I have. So it's being able to find those locations. All right, we're going to try one more. And again, thinking about what's important on a graph here. So let's try this last one. We have an x squared minus 4 over an x squared minus x minus 6. So here's our function. Okay, so take a peek at the degrees. So the degree in the numerator is 2. The degree in the denominator is also 2. Okay, what does that tell you for horizontal asymptotes? The degrees are equal. So what does that mean? That means it goes to the ratio of the leading coefficients. So 1 over 1, it looks like we should have a horizontal asymptote at 1. So for a lot of people, that's kind of one of the easier things to identify right off the bat. Okay, let's see if we can simplify this fraction. When you have bigger degrees like this, that's what I'm suspect about things being able to be divided out. And this will also help us with our domain, so we can do that as well. So we'll talk about domain, thinking about that denominator, and we'll also do the factoring. So how do you factor x squared minus 4? So x and x, and we need to multiply to negative 4 and add to 0, so negative 2 plus 2. And then on the bottom, x and x, go ahead, pause the video, factor the bottom. So multiply to negative 6, which means our signs are opposite, and they are going to add to negative 1. So minus 3 plus 2, and it looks like we're going to be able to reduce this fraction. So it should reduce down to x minus 2 over x minus 3. Okay, that's a really critical part in our discussion, because that means setting that denominator equal to 0, I have 2 excluded values, no question. X equals 3 and x equals negative 2. Absolutely, I have 2 factors in the denominator. Only one of them, though, is going to generate a vertical asymptote. If I remove that x plus 2, which is the negative 2 solution, that can be reduced out. This is a point discontinuity, or it's a hole, or it is a removable discontinuity. It does not leave a vertical asymptote. So it's an excluded value from the domain. Absolutely, the domain is all real numbers. X can't be either of those. Can't be 3, can't be negative 2. That's a 2. But the x equals 3 is the only vertical asymptote in this scenario, because it's the one that you're stuck with, right? You still have that x minus 3. It's still a place where you're not going to have a value of the domain, but it's the only one that's going to give you a vertical asymptote. So x equals 3 is your only vertical asymptote. Negative 2 is a point discontinuity or a hole in the graph. So be careful about that when you're doing points and values, because that's not going to be a place on the graph that's going to have any function value. So x equals 3 is our only vertical asymptote. So just be super careful. Make sure you simplify first. So x equals 3 is our vertical asymptote. All right, so let's take a peek and see if we can find our intercepts, because that'll help us with some points on the graph as well. Y-intercept, remember, it's plugging in as 0 for x. So 0 squared minus 4 over 0 squared minus 0 minus 6. Looks like that's going to put me at negative 4 over negative 6, 2/3. So we have the point 0, 2/3 on the graph, so that's helpful. So 0, 2/3 would be about there-ish. Okay, let's see if we can do an x-intercept. That's solving this equation, setting 0 equal to, and then solving. Now remember, it doesn't really matter what your denominator is here, because you're going to multiply both sides by it first. So you're really just solving 0 equals x squared minus 4. Now when you solve that, technically, you're going to move the 4 over, or you can solve it by factoring square root. Technically, you're going to get plus or minus 2. Now here's the issue. Negative 2 is an excluded value in your function, right? It's not a value that we can use because of the denominator. So really the only x-intercept then is going to be at positive 2, because negative 2 is going to be a hole. So just be careful. You will not actually have an x-intercept at negative 2. It is a hole on the graph. So just be super careful about your domain. Always go back to that. So the only one that's going to be an x-intercept is going to be at 2. So that's a point on my graph. So it gave me a couple. So I have a couple points that are going to be helpful, but I don't have enough to see the whole graph. So I'm going to need some additional points. So let's take a peek and see if we can get some more points here on a table. Now, it would be helpful to see something then bigger than 3, right? Because we want to see what's happening on the other side of that vertical asymptote. And when you think about what's happening here, hopefully you can tell. Remember what vertical asymptote means. It means it approaches negative infinity there. At negative 2, just be cautious. That's the hole. So when we sketch this, that should be an open circle, trying to make that an open one. So this is your hole right there at negative 2. It should not be filled in, so just be careful. That should be an open circle there at negative 2. Let's try to see a number on the other side here. So can you plug in 4 into that equation and see what you come up with? So I went ahead and put that into my graphing calculator and then go over to my table here at 4. It looks like it's 2. And then you can see where it says error at -2, error at +3. Those are our 2 excluded values. Remember, only one of them gave you a vertical asymptote, but at least I know another point here. So 4, 2, and I know what asymptotes mean, so I can go ahead and fill those in. Go ahead and peek back now at the actual graph of this one. It looks like what we have. Now, here's the cool thing again, at -2, I know you can't really tell, but if we zoom in on that negative, oh, not zoom, I want to do my own window, go from like say -3 to -1, you're going to see that hole, right? And remember the difference, if you had graphed instead this, there wouldn't be the hole there, but we know from the original equation there is a hole there. The x minus 2 over x minus 3, if you graph that instead, that's going to give you the exact same so exact same picture, just no hole. So watch when I do this graph. See how it fills it in there? So just be aware that the graph that we have does have the hole. That's the whole idea. Get it? The whole idea? Yeah, the whole idea of understanding what holes are. So making sure we know how to do that. All right, so let's go back to our essential question for today. How can I sketch the graph of a rational function? Well, it goes back to listing all of those critical features, y-intercept, x-intercept, the vertical and horizontal asymptotes, getting enough additional points so you can see what's happening in between. But don't ever forget about your domain. Always start with that and simplifying the fraction first so you know what are asymptotes and what are just going to be holes.